Good afternoon, guys. Am I audible?
Yes, sir.
Yes, sir.
We'll get started. So I think we have completed the second part of magnetism, right? Yesterday we saw hysteresis loop also. Right? So is there any doubt from the topic we discussed yesterday?
No, sir.
Okay. Okay. Today we are going to discuss the last part of the chapter, that is, we call it as Earth's magnetism. Okay. So let's see what the topic is all about. So please write down the heading as Earth's magnetism. Okay. See, in a real-time basis, suppose, let's say we are traveling, right? So when you're traveling, let's say I give you a compass and you're standing in a particular location, some random location, okay? And if I give you that compass, what will happen is you can see that there will be some deflection taking place in the compass depending on where you stand. As you keep moving, the deflection might keep changing. Okay. Have you ever observed it? Right. So how is it possible? Why is the compass needle experiencing deflection at different locations? So first of all, we need to know the basics of a compass. What is a compass needle made up of?
Bar magnet, sir.
Yeah, it's a small bar magnet kind of thing, right? Right. We can say it responds to magnetism. So compass needle is able to revolve because it responds to magnetism. Now the question is, when you're randomly walking on the surface of Earth, then how is the compass able to experience torque? So when I say it responds to magnetism, it experiences torque. It is then this pointer can revolve, right? Torque is the effect for revolution. Now, who's providing the necessary magnetism for this needle to experience the torque and revolve? That's what is done by the Earth's magnetism. Okay, that is what the topic is all about. Right? Now the question is, let's revisit the basics again. I have told you multiple times that for you to have magnetism, what is necessary? For you to have magnetism, natural magnetism or man-made artificial magnetism to exist, what is needed for us? What is supposed to be ensured that you can say that yes, magnetism will be present in this location? Guys, I've told this many times. That is the basic with which we started this chapter.
So could you repeat
What is
again?
it? I'm saying, what is the necessary condition for magnetism to exist? When can you say magnetism will exist?
When there is electrical field.
When there is, you're almost there, completed. When there is electrical
Field, sir.
No. Electric field is due to the charges at rest. I've given you the hint.
Static
So
electricity, sir.
No. When you have charges in motion, guys, don't forget this. This is the base. So wherever you see magnetism is existing, then you can conclude that there are some charges which are flowing. Okay. Now the question is, see, we discussed about an electromagnet in the previous chapter. When you take a wire, a conductor, and connect it across the ends of a battery, then electrons will flow within the conductor, due to which you are able to observe magnetism. Means you place a compass near to it, you can see that the compass will experience some deflection. Or if you take some iron particles close to it, ferromagnetic substances close to an electromagnet, the ferromagnetic substances tend to get attracted. Right? In a similar way, we saw what is the reason for permanent magnetism. What was it? So what was the reason for permanent magnetism to occur? It is because of the magnetic dipole moment getting generated due to the revolution of electrons in atom, right? In a similar way, for Earth's magnetism also, we need certain charges to be in motion. But the question is, there is no concrete theory of why this is happening. Okay. So till now, there is no concrete reason for the cause of Earth's magnetism. There are different theories that are proposed based on the basics of what will generate magnetism. Okay. So there are few theories that revolve around it. Some of the theories are mentioned below. Let me read out all the theories that are there, based on which we will see which one is close to the reality and which one is more acceptable. Okay. The first one is called as the dynamo effect. So the dynamo effect speaks about some molten iron particles present in the outer core of the Earth. See, in the outer core, what happens is we have molten iron and other heavy metals in liquid form. So generally, when they are in liquid form, they have the tendency to flow, right? So the inner core, what it does is it solidifies under the influence of gravity. So therefore, what will happen is the motion of metallic fluids in the outer core of the Earth causes an electric current. This effect is what is called as dynamo effect. And this is the reason why they say there are magnetic field lines around the Earth. So this is the reason why Earth gets its own magnetic field lines. Okay, this is one of the theories that is proposed. And the second theory is about the ionization of the outer layers. We know what is ionization, right? Conversion of an element into an ion by losing or gaining of electrons, right? So this theory tells us that the rotation of Earth in its own axis will produce a strong electric current due to the ionization of the outer layers of Earth. Okay, so due to this electric current which is getting generated, which is a result of the Earth's rotation, is what is the reason for magnetism exhibited by Earth. So this produces magnetism due to the movement of the ions. However, the magnetic field will be very weak. But what happens is, in reality, the dynamo effect is the more acceptable theory. Okay. So based on the value of the field, Earth's magnetic field found at different locations, if you observe the Earth's magnetic field in real time, right, it will be in terms of few Gauss. Okay. So that kind of a possibility and the theory that is proposed, the more accepted theory is this dynamo effect. Okay, so have this in your mind and don't worry, nobody is going to ask you what is the reason behind the Earth's magnetism. Nobody will ask you, because as the theory itself is not clear. It is only for your knowledge. Okay, now you can ask me, what is that we are going to learn under Earth's magnetism? The main topic with respect to the subject and the exam perspective, if you see, the main topics that we are going to concentrate upon is the elements of Earth's magnetism. So there are basically three elements that are associated, elements, or we can say components. So there are three components of Earth's magnetism. Some books refer to it as elements also. Okay. Now, further, there are certain theories that you need to know again. Okay. So just give me a second. I'll show you a small simulation. 1 minute. It's not opening. Anyway, let me check after 2 minutes. In the meanwhile, let's discuss from the book itself. Listen, guys. So if you observe the Earth's magnetism, here you have Earth, right? So we can assume as if there is a bar magnet present extending from the north pole of the geographic north of the Earth to the geographic south in such a way that if you try to draw the field lines, the magnetic field lines generated due to the Earth's surface, you can observe that the magnetic field lines due to the Earth will be from the geographic north to the geographic south to the geographic north. Right. What I'm trying to say is, if you take this as Earth, okay, listen to this carefully. There is a tricky concept. If you take this as the Earth, right, and this Earth has certain parts associated with it. So what is this called, guys? This is an imaginary line that is going to pass through the topmost point and the bottommost point. This is generally called as the value Ng. What does Ng stand for? It is called as geographic north, and this part is called as the geographic south. Are you guys able to understand? So if there is an imaginary line passing through the geographic north and the geographic south, then this is called as the geographic axis. Am I clear with this?
Yes.
Okay. Now, what happens is, if you try to draw the field lines, as I told you, the field lines will start from this geographic north pole and they will go towards the geographic, did I say north? Sorry. They start at the geographic south pole and go to the geographic north pole. Means the magnetic pole which is close to the geographic north is actually the south pole. I repeat it. Listen to this carefully. The magnetic pole which is close to whom? The magnetic which is close to the geographic north pole is what? Is the magnetic south. Are you able to understand?
Yes, sir.
Right? So that is how, in reality, in today's world, that is how the magnetic field lines are going to exist. But there was a small confusion. What happened? When they were giving these naming structures, right, initially when this kind of an effect was observed, even before these field lines and everything was drawn, what happened is, they thought that the geographic north and the magnetic north are the same. And they call the geographic north also close to the magnetic north. But what is the reality? When we say magnetic north, actually what pole are we referring to? You are actually referring to the south pole of the magnet. This is the most important point. Okay, there is a confusing factor. In many books you see, no, you will get confused if you read it. So I repeat it again. The pole, the magnetic pole which is close. I'm not saying the magnetic pole which exactly coincides. That will not happen. Okay. The magnetic pole which is close to the geographic north is actually the magnetic south. But in the naming structure, how do they name it? They write it as NM. Okay. Because this was a naming convention given even before all this theory was invented. So they have not yet changed it. So this is how it is universally followed. You're able to understand? So this is what we call it as NM, and this is called as SM. So M stands for magnetic, G stands for geographic. Have this point in your mind. Okay. Now comes another important question. So if you draw an imaginary line passing through the geographic north and the geographic south, what is it called as? We call it as geographic axis. Whereas if you draw an imaginary line passing through the magnetic north and the magnetic south, then this line will be called as, can you guess it? Imaginary line is axis only. Can you guys guess it?
Magnetic axis, sir.
It's called as magnetic axis. It's called magnetic axis because it is passing through the magnetic poles. Am I clear, guys? So before we see the three components which I mentioned, the first thing that you need to understand is what is geographic axis and what is magnetic axis. Okay, so please write it down. These are the first two terms that we are going to learn. I want everybody to write. So first point is geographic axis. Write it down. It is an imaginary line passing through the geographic north and the geographic south. Okay. An imaginary line passing through the geographic north and the geographic south is called a geographic axis. Then write what is magnetic axis. An imaginary line passing through the magnetic north and the magnetic south. Am I clear, guys?
Could you repeat for magnetic axis?
An imaginary line passing through the magnetic north and the magnetic south. Clear?
Okay, sir.
Okay. So this is all about axis, guys. There is another term that we deal with. It's called as meridian. Okay. So let's see what a meridian means. So meridian is also of two types. One is geographic meridian and the second is called as magnetic meridian. So generally when we use the word axis, what comes to your mind? Is it one dimensional or two dimensional? Magnetic axis is basically one dimensional, and this is also one dimensional. Whereas when you talk about meridian, it is two dimensional. What is the technical name given to two dimensional shapes? We call them as planes, right? So write it down. A plane passing through the geographic north and geographic south. The plane passing through the geographic north and the geographic south and perpendicular to the geographic axis is called as geographic meridian. Geographic meridian. Right? So if you replace the word geographic with magnetic, that will become the magnetic meridian. That point also you make a note of. Please write it down. Done? Done, guys?
Yes.
Okay. Now, we are going to discuss about the components of Earth's magnetic field. So these are all the information that we need to give to find the location. See, for example, you're having a compass in your hand and you want to travel in a particular direction, then you need to know certain things with respect to the Earth's magnetism at the location in which you're there, so that your travel will be even more smoother. Okay. So near the surface of Earth, what will happen? if you take the magnetic field, they are curved, right? The magnetic field is obviously curved. But if you want to find the direction of magnetic field at a particular point, what do? We draw a tangent at that particular point in the direction of magnetic field. Right? So near the surface of the Earth, the magnetic field of the planet can be resolved in different directions. Okay. So there are certain components which are responsible for the magnitude and direction of the magnetic field of the Earth at a given location. Okay. So there are certain reasons. And the first one is called as magnetic declination, or we call it as magnetic variation. Okay, magnetic variation, you cannot find it in your textbooks. The most common name that is used is magnetic declination. That is the first component of Earth's magnetism. The second component of Earth's magnetism is called as the horizontal component of Earth's magnetic field. See, generally the magnetic field at a particular location can be resolved into two components. One is vertical, one is horizontal. Okay, but we will be concerned about the horizontal component of the Earth's magnetic field. And the third is called as the angle of dip or magnetic inclination. Okay, don't get confused between the first and the last. The first one is called magnetic declination, and the last one is called as the magnetic inclination. Okay. So first, let's see what magnetic declination means. See, one thing that is fixed is the geographic axis. The geographic north and the geographic south are fixed, and the axis is going to be fixed. But what keeps changing at different locations is, depending on which part of the Earth you're standing, the magnetic axis keeps changing. Okay, that is what is observed. And when the magnetic axis is changing with respect to the geographic axis, then you can find a small angle between them. Okay. And that angle that is existing between the geographic axis and the magnetic axis is what is called as magnetic declination or magnetic variation. So please write down the definition. Magnetic declination is defined as the angle made by the magnetic axis is also right, meridian is also right. Magnetic declination is defined as the angle made by the magnetic axis with the geographic axis. Okay. Or in your school, if your teacher insists to write meridian, then go with it. Both are right. Okay. So magnetic declination is the angle made by the magnetic axis with the geographic axis. Okay. So that is the first point. Second, before I explain the horizontal component of Earth's magnetic field, we will discuss about what is angle of dip or magnetic inclination. See, for this I have to show you something. So listen, guys. See, if you hold any object, you take and you hold any object about its center of gravity. So how will you find the center of gravity of any object? You try to hold it at a different point without applying pressure. You keep moving from one end to another. There will be one particular point at which you can see that it will not revolve. So with respect to the object I have in my hand, this is the center of gravity, right? So what I'm trying to say is, at the center of gravity, if an object is suspended, right, it should experience how much torque? It should experience zero torque, right? Whereas if you look at the compass needle will be in the shape of the diamond, okay? and the compass needle will be suspended exactly at the center of it, then what is supposed to happen to it? It is not supposed to move in this way. Am I right? Are you able to understand what I'm trying to say? Because it is exactly hinged at the center. So when it is the center of gravity of that particular needle, it is not supposed to move in this path. Guys, am I clear till this point? Did you understand the significance of center of gravity? Yes or no?
Can explain again, sir?
When you hold any object about the center of gravity, it should not oscillate or it should not rotate. This should not happen or this should not happen. Okay. So when you take a compass needle, the compass needle is suspended exactly at its center. Right. So due to the Earth's magnetic field, the compass is supposed to revolve like this. So when you see from the top, the compass will be revolving in this way. Right? Are you able to observe what I'm trying to say? It will revolve like this. Right? But due to the revolution, during the process of this revolution, which is supposed to rotate in this plane, it is supposed to rotate in the horizontal plane. But what will happen in reality is, while it is experiencing a revolution like this, it will experience some oscillatory motion also. Means, though it is hinged at the center of gravity, it is experiencing a torque in the vertical plane also. So due to that oscillation, what will happen is, with respect to the horizontal, at some instant, it might be like this. If you take a pic of it and a slow motion picture of it, okay, if you take a slow motion capture of that particular motion, then you can see at one particular instant, it will be like this. Okay. When it is in this form, then if this is the direction of magnetic field, okay. So magnetic field, we told that compass is made up of a magnetic needle. So for a magnetic needle, what is going to be the direction of magnetic field? If this is the north pole of the needle, south pole of the needle, north to south outside it, south to north inside it. So this is going to be the direction of magnetic field. It is the direction of Earth's magnetic field. Then what will happen is, when the compass is experiencing an inclination in this way, then it is going to make some angle with the horizontal. Who is making the angle? It is the magnetic field of the Earth which is making an angle with the horizontal, and this angle is what is called as angle of dip or angle of inclination. Okay, so why is it happening? It is because, see, had the compass been revolving like this, compass needle been revolving only in the horizontal, sorry, I'm not able to revolve it. If it is revolving only in the horizontal plane, then this kind of a motion would have not taken place. So it will revolve like this actually. So it will revolve in this way. So it keeps oscillating and it will keep revolving. Okay. So the angle which the Earth's magnetic field is making with respect to horizontal is what we call it as the magnetic dip, or sorry, the angle of dip or magnetic inclination. Okay. So that's what the definition is. Please write it down. So take a magnetic needle and suspend it freely. So when they say suspend it freely, suspend it about its center of gravity so that it can rotate about a horizontal axis as shown in the diagram. So you're able to understand. The magnetic needle, it is not like this. Rather, it is making some angle. Then, if this is the direction of Earth's magnetic field at that location, if I call this as BE, then this BE will make an angle with the horizontal, and this angle is what we call it as angle of dip, and it is represented by the symbol delta.
Sir, what is that horizontal and vertical, sir?
Components, resolution. So BE can be resolved into two components. One is horizontal component and the vertical component. And this is what we call it as the horizontal component of Earth's magnetic field, written as BH, And this is what is written as BV, and this angle. So angle of dip is measured between whom? Angle of dip is measured between the Earth's magnetic field and it is there in the
horizontal component.
Very good. And its horizontal component. Okay, it is represented by the symbol delta. So the other name for angle of dip is, it is called as angle of inclination or magnetic inclination also. So please make a note of it. So the angle that the north pole of the needle makes with the horizontal axis called as the angle of dip or magnetic inclination. Okay. And what is the third component, guys? Third component we have already seen. What is it? The horizontal component of Earth's magnetic field is what is the third component. So what will be the value of BH? BH will be equal to BE into cos delta. What is BE? BE stands for Earth's magnetic field at a particular location. Okay. Now, we will see how to calculate the Earth's magnetic field at a, we'll try to figure out a formula for the Earth's magnetic field at a given point in terms of angle of dip. So remember, this is the Earth's magnetic field at a particular location. This is the angle of dip. Okay, and this will be the horizontal component and this will be the vertical component. Okay, so BH will be equal to how much? It will be BE cos delta, and BV will be equal to BE sin delta. Okay, sometimes what will happen is all these formulae are related except angle of inclination, except magnetic declination. You can see that the other two components are related. That is the angle of dip and the horizontal component of Earth's magnetic field are involved. Now, what will happen is sometimes they will give you the value of BH and BV and ask you to calculate the angle of dip. Then what we can do, divide these two expressions, then you will get tan delta is equal to the vertical component divided by the horizontal component. Are you able to understand? This is one of the formulae. So once you calculate this value, you will get the value of delta. Delta will be tan inverse of BV by BH. That is one way. Or the other formula is BE will be equal to root of BV square plus BH square. Why? When you apply the parallelogram law of vectors for both, you can observe since they are perpendicular, horizontal and the vertical are perpendicular, the resultant will be root of A square plus B square. That is BV square plus BH square. Okay, so these are all the formulae that are related to the Earth's magnetic field. Am I clear, guys?
Could you show the derivation?
Which derivation? There is no derivation. This one. Don't look at this, you will get confused. There's the part, there is no derivation. It is just application of parallelogram law of vectors.
Okay, sir.
Yeah. Okay. Just give me a minute. I'll Try to open a sheet of problems. We'll do some example problems. And with that, we're done. So I've taught everything that is needed for your CBSE exam test. Nothing more than this is needed. Okay. Let's now. So we know with respect to Earth's magnetism, we don't need to study about neutral points. Neutral points is not there for CBSE. So we know what is declination, right? It is the angle between the geographic meridian and the magnetic meridian, or you can write it as geographic axis and the magnetic axis. Both mean the same. Second, relation between the elements of Earth's magnetism. BH is equal to B cos delta, where B stands for Earth's magnetic field, and BV is equal to B sin delta, and BV by BH is equal to tan delta, and B is equal to root of BV square plus BH square. Then you don't need these neutral point concepts, you can forget. Okay. Now, let's do the first question. So the declination at a place is 15 degrees west of north. So what do you mean by 15 degrees west of north? See, there is an important point you need to concentrate on. Okay. So when they say 15 degrees west of north or 15 degrees, or they say northwest. So there are two things, right? This will confuse you always. So what do you mean by northwest? If suppose in a question they are saying northwest, what do you mean by that?
In between north and west.
Between north and west, by what angle?
Sir.
Exactly 45 degrees. So if they give the word northwest, then it is exactly 45 degrees with north and west. Okay. Now what is the question? Here you have North Pole, South Pole. Here you have east, here you have west. So the declination at a place is 15 degrees west of north. What do you mean by that?
From north to 15 degrees.
Yes, from north towards west means in anti-clockwise direction, the magnetic declination is 15 degrees. Means it is like a zero error. Right? If you read the question carefully, where is a person willing to reach? Where is a person willing to go? The person, they want to go to east. Okay. And the angle of declination be 0 degrees. At the angle of declination be 0 degrees, then in what direction will he move? Exactly at 90 degrees with respect to north. But what is happening? There is some error occurring at that place because there is a variation, right? So there is an angle existing between the geographic axis and the magnetic axis. So it is 15 degrees. So at what angle is he supposed to steer so that he is able to reach due east? Is it not 90 plus 15, which is 105 degrees? And that is the answer. You're able to understand. All these deserve only 1 mark. Okay, these are all 1 mark questions. But I hope you understood what exactly do I mean by magnetic declination. So when there is no coincidence existing between the magnetic axis and the geographic axis, then there is, for your understanding, I'm using this word that is not right. It is like an error. It is like a zero error that is occurring. Okay, it is because they both are not coinciding. To make that zero error into a correct path, you need to rotate it in particular directions. Okay, based with the same knowledge, I want you to try the second problem. A ship is to reach a place 10 degrees south of west. Draw the diagram. 10 degrees south of west means from south, tell this right, from south towards west, in which direction? Clockwise or anti-clockwise?
Clockwise, sir.
Very good. So clockwise. Okay. So there's north, there's south, there's east, there's west. So a ship is to reach a place 10 degrees south of. He wants to reach this location. He wants to travel in this direction, 10 degrees south of west.
So I
In
have,
which tell me.
shouldn't 10 degree be with respect to west, sir?
No. Oh, 10 degrees south of west. Oh, sorry. I'm sorry, you're right. So 10 degrees south of west means from west 10 degrees in this direction. Okay. In which direction should it be steered if the inclination at the place is 18 degrees west of north? So magnetic declination is 18 degrees west of north. So how much is this angle supposed to be?
72 degrees, sir.
72.
Yes, sir. 72 plus 10.
So you understood, everyone. So this is 72. If it is steered at 72 degrees, he will reach exactly west. But what is the required destination? 72 plus 10 degrees. It is then he will fall on this particular line. So I hope you understood, right? So it's all about drawing the right diagram. That's it. That will give you the answer. Are you clear, guys?
Yes,
So this is about magnetic declination. Okay, let me see if this question is a magnetic meridian. Okay, let's try to do this. In the magnetic meridian of a certain place, the horizontal component of the Earth's magnetic field is 0.26 Gauss and the angle of dip is 60 degrees. What is the magnetic field of the Earth in this location? Guys, find it out. It's a one-step question, trust me. What have they given? The horizontal component is 0.26 cos. Angle of dip is 60 degrees. So what is the value of BH? BH is equal to BE times cos delta. BH is 0.26. BE is what is to be found? Cos of 60 degrees. How much will be the answer? BE divided by 2 into 0.26. If this comes this side, BE will be 0.52 cos. Simple. So the answer is 0.52 Gauss. Clear, guys?
Yes, sir.
Okay, let's try this. This is a slightly hybrid question, means combination of two concepts. Let's try this. No? There is a compass needle whose magnetic moment is 60 ampere meter square, pointing geographical north at a certain place where the horizontal component of the Earth's field is 40 micro Weber per meter square. I hope you guys remember this. When I explained the concept of magnetic induction, I told magnetic induction is either measured in terms of Tesla or Weber per meter square. So here it is 40 micro Weber per meter square. So the Earth's magnetic field can be taken as 40 into 10 power minus 6 Tesla also. I hope you guys understood this. Weber per meter square is the same as Tesla. Okay. And it experiences a torque, one minute, where the horizontal component of Earth's magnetic, horizontal component of Earth's magnetic field is this much. Torque is 1.2 into 10 power minus 3 Newton meter. What is the declination of the place? The declination of the place. I think it should be inclination. Let's see. So a compass needle whose magnetic moment is this much. So torque is equal to, what is the formula? mb cos theta, where theta is the angle between the magnetic dipole moment and the magnetic field. So if BH is this much, then torque is 1.2 is equal to M is how much? 60 into B is 40 into 10 power minus 6 into cos theta. Let's see if we are able to get the answer.
Sir?
Tell me.
Sir, B is the magnetic field of Earth, right?
No need, because here the horizontal component is what is producing the torque. Are you able to understand? So the horizontal component is what is producing the torque. So this will be 500, 12 means it is 550 here. This will be 120 by 100 or 12 by 10. So this will go 5 times, so 50. So cos theta will be equal to 1 divided by 2000 into 10 power minus 6. So how much is the answer? My answer should not be this much big value. 10 power minus, oh, I forgot 10 power minus 3 here. So it will be 1.2 into 10 power minus theta. So 1.2 will cancel this 15 times, 10 power minus 3 will cancel this 3 times. So 10 power minus 3. Here it is 10 power minus 3. This and this will get cancelled. So 1 by 2 will be the answer. So they are asking what is cos delta equal to? Cos delta will be asked. And the angle of dip at that particular location will be 60 degrees. Okay. Please make a note of it.
Sir?
Tell me.
Sir, how will we know whether to calculate the magnetic component? So that is not that horizontal or vertical, the total magnetic field, B, sir, B, E,
They'll
sir,
ask in the question. The question itself will tell you. Like how we did the previous problem. They asked, no, what is the magnetic field of the Earth in this location? The question will be clear about it. Okay, here what happened, it experiences a torque due to the horizontal component. That is why I wrote this formula.
Okay, sir.
Could you go up for the second?
Sure.
Yes, sir.
One last problem. See, for example, you ask this question, no? The horizontal and the vertical components of the Earth's field at a particular location are 0.22 cos and 0.38 cos respectively. Calculate the angle of dip. For angle of dip, what is the formula? Tan delta is equal to BV divided by BH. So what is BV? 0.38 divided by 0.2. That is 19 divided by 11. Delta is equal to tan inverse of 19 by 11. Okay. Now they are asking the resultant intensity of the field. So BE will be equal to root of BV square plus BH square. So what is BV square? B 0.38 the whole square plus 0.22 the whole square. Okay. So that will be the value of the Earth's magnetic field. If you calculate it, it will come out to be 0.427 cos. Clear, guys?
Yes.
So these are all the maximum variations of problem that you get in our boards. Nothing beyond this. Okay, they're not complicated because this topic, not many questions are asked. Generally, they will ask you theory, but very rarely if they ask problems also, I'm sure now you guys can handle it. Right? That's it, guys. So that's all. You need not worry about any other problem also. So these are all the maximum variations that you will have. Okay. So I hope it is clear, right? And the conclusion is this chapter is over. Chapter 5 is over. Okay. Next class, I'll start chapter 6, that is the electromagnetic induction. Okay. So be ready for it. And also, I wanted to mention that since chapter 4 and chapter 5 are also over, I'll be announcing tests for it. So be prepared. Keep preparing and ensure you are ready for the test as soon as I announce it. Okay. Any other doubt, guys, from today's class?
No, sir.
No doubts, sir.
Good. You can wind up.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.